So welcome back. We have two problem sheets pending, right? The assignment for the last week, this week and the previous week, right? Am I right? So let's quickly work out those problems, shall we? We are on problem sheet number 20. I request everyone to take problem sheet number 20. Problem sheet number 20, can you take problem sheet number 20? And by the way, please listen carefully. This is regarding the class for next week. The next week is the Easter Sunday. So we have three options. One is we can conduct class as usual. That is option number A. The second option is we can cancel the class for the week. Third option is we can cancel the class on Sunday and keep it on some other day of the week. So what do you suggest? We have three options. One is conduct the class as usual. It's a matter of just 1 hour. Second is cancel the class for the week. The third one is cancel on Sunday and keep on some other day. So can you let me know your opinion? A, B, C. One is cancel altogether. Second is cancel on. Second is one is conduct as usual. Second is cancel altogether. Third is cancel on the way. Yeah. We are talking about the next week, the Easter week, Easter Sunday. Please let me know your opinion. We'll do something which is comfortable for everyone. If it's okay for everyone, we can conduct as usual. It's just a matter of 1 hour, right? I'm talking about next Sunday. Yeah. What about others? Anjali, Olivia, Robin. Yeah. Others? Olivia and Robin. May I get an answer? No, we are talking about cancelling the class on next Sunday, and then we will move on with the next Sunday onwards as usual. But if everyone is okay with it, let's just continue with the classes because it's just a matter of 1 hour, right? Not a big deal. Anyway, okay. I'll let you know in the group. Yeah. So we are on problem sheet number 20. Please take problem sheet number 20. We were dealing with linear functions. So first question. These are all simple questions, okay? We are just discussing basic ideas from linear function. Then we will move on to word problems. Which of the following does not represent a linear function? Okay. And as we know that a linear function, when represented as there are multiple ways to represent a linear function. You can represent them as a graph. You can represent them as a set of ordered pairs. You can represent them as an input-output table. You can represent as a relationship between x and y. So when you represent a linear function as a relationship between x and y, it should always be in the form y is equal to mx plus c, or ax plus by plus c is equal to 0. Right? So this is in the form of mx plus c. This is also in the form of mx plus c, just that c is 0. That's not an issue. This is also in the form of mx plus c. Okay. But y is equal to 8 over x is not a linear function. y is equal to 8 over x is not a linear function. Y is equal to 8 over x is not a linear function. This does not represent a linear function. So if you plot the graph of y is equal to 8 over x, you're not going to get a straight line. Can you guess what will be the shape of this graph? Shape of this graph, y is equal to 8 over x. When you plot y is equal to 8 over x, what will be the shape of x? Shape of the graph? I'll just show you. So if you plot y is equal to 8 over x, what you're going to get is something like this. See? Nice, na? This is what we call a rectangular hyperbola. Rectangular hyperbola. Okay, you learn about this stuff in higher classes. Don't worry about it for the time being. It's called a rectangular hyperbola. So this is the right answer. Next question. Which of the following graphs represent a linear function? Which one represents a linear function? Is this a linear function? No, this is not a linear function. Okay. What is the shape of this graph? What is the shape called? In option A, what is that shape called? What is that shape called? Can somebody tell me what is that shape called? Hello? What is that shape called? If you know the answer, please let me know. If you don't know the answer, just say you don't know. I would like to get a response because it's difficult to move ahead with the class without getting any response from you. Yeah, others. Yeah, this is what we call a parabola. Okay, this is what we call a parabola. So instead of a linear function, if you have a quadratic, if you have a quadratic, you are going to get a parabola. I mean, we'll come to quadratics later on. For the time being, we are talking about only about linear functions. What about this? What about this? This is also again a parabola. It's actually a part of the parabola. It's actually a part of the parabola. Okay. But this is also not a linear function because, I'm sorry. This is also not a linear function because it's not a straight line. And what about third one? Third one, you see that it's a straight line, but there's a catch. You know what does this represent? This represents the equation x is equal to 3. Why? Because the x coordinate is 3 everywhere. You can see that if you take any point on the graph, the x coordinate is going to be 3. Y coordinate keeps varying, but the x coordinate is always 3. So this is a straight line, but there is a catch. This is not a function. Why? Because in a function, for one x value, you cannot have multiple y values. For one input, you cannot have multiple outputs. One input cannot produce multiple outputs. Okay. One input cannot produce multiple outputs. Always remember this. For a function, if you plug in a number into the function, if you feed a number as the input to the function, it will not produce more than one output. But it is okay for the function to have same output for two inputs. Same output for two functions is okay. For example, if you have f of x is equal to, so y is equal to x square. So if you feed x is equal to 3, this is going to give me y is equal to 9. If you feed x is equal to minus 3, then also it is going to give me y is equal to 9. This is okay. Two different inputs can have the same output. That is fine. But one input cannot produce multiple outputs. So here it is like a single x values taking multiple y values, which is unacceptable in a function. So this is not a function. We don't call this a function. Okay, this is not a function. And in the fourth case, we have a straight line. It's a normal straight line. So this is going to be a linear function. This is going to be a linear function. Okay. So the answer is going to be, in this case, the answer, which of the following represents a linear function? Which of the following represents a linear function? The answer is going to be D. The answer is going to be D. Okay. Cool. Shall we move on to the next question? So by looking at the graph of a function, how can you know that it's linear? It has to be a straight line. But remember, if you have a vertical line, it is not a function, because for one input is taking multiple outputs. It cannot be a function in the first place. Okay. Right. Now next question, question number 3. Which of the following ordered pairs represent a linear function? Okay, that's an interesting question. There are multiple ways to represent a function, a linear function. And we have seen a graph can be used. Now they have given ordered pairs. So we have already discussed that in a linear function, if it is represented by set of ordered pairs in the form of input comma output, x comma y, ordered pairs. If you have ordered pairs x comma y, how will you figure out that it will represent a linear function? How will you figure out that it represents a linear function? Okay, in a linear function, the idea is, if you take constant differences in x values, the differences in y values should also be a constant. Okay, if you take constant differences in x values, the differences in y values should also be a constant. So that is the idea we have discussed in the previous class. So let us take one by one. So in the first case, so let us try to represent this as a table of values. Let us represent this as a table of values. Instead of writing them as ordered pairs, let's create an input-output table. So we have inputs here, outputs here, corresponding to -2, which is 7, corresponding to -1, it's 4, corresponding to 0, it's 1, corresponding to 1, it's -2, corresponding to 2, it's -5. Now look at this input-output table. This is option number A, okay? This is option A. Now when going from -2 to -1, your x value gets increased by 1. Correspondingly, your y value gets increased by 3 here. Here, the x value gets increased by 1. Here, y value gets increased by, it gets increased by -3. I'm sorry, it gets decreased. The y value is decreasing. Here again, its y value is decreasing by -3. Here, x value increases by 1, y value decreases by -3. X value increases by 1, y value decreases by -3. See, it makes sense, right? This perfectly matches our condition. If you take constant differences in x values, the corresponding differences in y values are also constant. If you take corresponding differences, if you take 1 as the difference between x values, the corresponding differences in y values are all -3. So is that a linear function? Is this a linear function? Is this a linear function? Tell me, please. Is this a linear function? Hello? Hello? Are you with me? Yes, it is a linear function. Why? Because the condition is if you take constant differences in x, corresponding differences in y has to be constant, same. It should not change. It's minus 3 here, then it has to be minus 3 here. It has to be minus 3 here, it has to be minus 3 here. That's all. Okay. So if you take, say, some other case, say, for example, I'll take one more case and show you that it's not linear. The first option is the right option. This is a right option. So the others will not be the right one. I'm going to take the other cases. I mean, let's check for at least one case. So we have minus 2, 6. Then we have minus 1, 3. Then we have 0, 2. 0, 2. We have 1, 3. Two, 6. Now what happens? From going from minus 2 to minus 1, it gets increased by plus 1. Here it gets increased by plus 1, gets increased by plus 1, gets increased by plus 1. Correspondingly, what happens here? This gets decreased by minus 3, decreased by 1. Here it is plus 1, it's plus 3. See, is this a linear function? Is this a linear function? Is this a linear function? No, no. Why? Because you take constant differences in x here. The differences here are not the same. Okay, unlike in the previous case. So this is linear. This is not linear. This is non-linear. Cool. So you can check for option C and option D as well. The answer will be option A. Yes, question number 4. Which of the following equations represent a linear function? Again, if you have a linear function, when it is represented in terms of x and y as a relationship between x and y, it has to be of the form mx plus y is equal to 0. Y is equal to mx plus c, or it has to be ax plus by is equal to c, or ax plus by plus c is equal to 0. Any of these forms. Okay, so this is linear. This is not linear because x and y are combined together. This has cubic term. This is not linear. This has terms in the denominator. This is not linear. It's not a linear function. So the answer is option A. Option A is the right answer. Question number 5. For h of x is equal to half x minus 3. So this is yet another way of representing a linear function. In this method, what we write is the function value. The output value is represented as the output value. So if I have h as the function, if I give x as the input, the output will be represented as h of x. It's not h times x, okay? It is h of x. So in this case, h of x is represented as a expression in x. Okay, this is what we call a functional notation. This is what we call a functional notation. So in this case, the output is represented as a function of x. The output is represented as an expression in x. So what is h of 12? H of 12 is going to be, instead of x, you just substitute 12. So this is going to be half times 12 minus 3. So this is 6 minus 3, which is 3. So the answer is 3. Got it? Yes. Next question, question number 6. Please listen carefully. Okay, this is very basic stuff, but to solve advanced level questions, you should be able to understand this basic stuff. Okay, these are basic stuff, but you should know this basic stuff to solve advanced problems. Which of the following ordered pairs do not lie on the function y is equal to half x plus 3? Which of the following ordered pairs do not lie on y is equal to half x plus 3? So y is equal to half x plus 3. Now you check each option. In the first option, if you take first option, y is equal to half times minus 4 plus 1. So this is going to be minus 2 plus 1, which is minus 1. So for x is equal to minus 4, your y value is minus 1. So this lies on the function. Why? Because when you put x is equal to minus 4, your y value is going to be 1. Okay? Is that all right? And the second option, when you put x is equal to minus 2, your y value is going to be half of minus 2 plus 3, which is minus 1 plus 3, which is going to be 2. That is also true. Okay. And the third option is, when you have x is equal to 2, your y value becomes half times 2 plus 4. So no, it's plus 3. So 1 plus 3 is equal to 4. So 4 is the right answer. Now, option D. In option D, your y value comes out as half times 0 plus 3, which is 3. Now, this is not matching. This point, this ordered pair does not lie on the given function. This ordered pair does not lie on the given function. So your question says, which of the following ordered pairs do not lie? Do not lie. So the answer is this. The answer is this. Is that okay? Is that okay for everyone? Is that okay, everyone? Everyone? Okay, yeah. In the next question, which function has 3, 2 on its graph? You just need to verify which function has 3, 2 on the graph. Just try to substitute 3, 2 here. 3, 2. So 2 is equal to 3 minus 1. Yeah. So this is satisfying. 3x plus 2y is equal to 12. So 3 times 3 plus 2 times 2 is equal to 12. So it's 9 plus 4 is equal to 13. It's not satisfied. 3x is equal to 2y. So this is 3 times 3 is equal to 2 times 2. It's not satisfied. Y is equal to minus 2 by 3x plus 4. So we have 2 is equal to minus 2 by 3 times 3 plus 4. 2. This is satisfied. Oh, I made a mistake here. See, I made a mistake in the first option. It's 3 here and it is 2 minus 1. This is wrong. Wrong. Option A is wrong. Option C is wrong. Option B is wrong. Option D is the right one. Okay, option D is the right one. Okay, it's pretty easy, right? You just have to substitute. When you have a point, when you have an ordered pair in the form 3, 2, it simply means that your x is taking 3 as the value, y is taking 2 as the value. Okay, that's all. Now you just substitute in the given equations and check which of them is satisfying the given ordered pair or given points. Now question number 8. Which of the following equations does not represent a linear function? Which of the following does not represent a linear function? Now here, listen carefully. Please listen carefully. Here, you look at every option. Instead of y as something in terms of x, we have x in terms of y. We have x in terms of y. Okay, we have x in terms of y. So we need to understand that if y is a linear function of x, if y is a linear function of x, y is a linear function of x, it also means that x is a linear function of y. Okay, what I'm saying is that if the relationship between y and x is linear, then the relationship between x and y will also be linear. Okay, why? Because if you take a straight line, now you suppose you change the axis, it will still be a straight line, right? It will still be a straight line. Okay, it will still be a straight line. For example, if you take this function. For example, you take this function. It's actually y is equal to 8 minus x. It's actually y is equal to 8 minus x, which is a linear function. Y is represented as a linear function of x. But you can also write this as x is equal to 8 minus y, which is exactly what is given in the question. Now this looks like what? X is represented as a linear function of y. Okay, these both are essentially the same. Okay, so idea is very simple. If y is represented as a linear function of x, x can also be represented as a linear function of y. Okay, so this is going to be a linear function of x, linear relationship between x and y. This will represent a linear function. This will represent a linear function. Here there is a catch. As I told you before, x is equal to 8 is a straight line, but it's a different type of straight line. So let's plot it. If I plot x is equal to 8, what are you expecting? If I plot x is equal to 8, what are you expecting? If you plot x is equal to 8, you are expecting a straight line, but it is a straight line, it's a vertical line. It's a vertical line. X is equal to 8 is a vertical line, it's not a function. It's not a function. Okay, because for one x value, it's taking multiple y values. For one input, there are multiple outputs. Okay, so this is not a function. We have seen this before. This is not a function at all. This is not a function at all. Okay. Okay, let's go to question number 9. The function represented by the below table is. Okay. Now we have a table given here. And I haven't really told you how to get the expression for the function from a given table. We will see that. We haven't seen that yet. Okay. Given a table of values, how do you find the expression? How do you get the graph? We have not discussed this yet. But in this case, it's much easy actually. You just need to observe things. There is x given in one of the tables, one of the columns. There is y given in one of the second column. Do you see that there is an obvious relationship between x and y values? Don't you see that there is an obvious relationship between x and y values? Do you see that? What do you observe from these numbers? Of course, there is a standard procedure to get the relationship, but this is a pretty easy one. Just by observing, do you see that there is a relationship between x values and y values? Do you see that? Yeah, what is the relationship? The y values are 2 times the x values, right? The y values are 2 times the x values. See, this is 2 times 0. This is 2 times 1. 2 times 3 is 6. 2 times 6 is 12, right? So we can write y is 2 times x. Y is 2 times x. Of course, there's a standard procedure to arrive at this answer. If things are not this easy, there is a standard procedure. I haven't discussed that yet. Do not worry. We will come to that. We haven't discussed that yet. So our answer is y is equal to 2 times x. Y is equal to 2 times x. Got it? Yes. Others, please let me know. Yeah, cool. Yes. Now let's look at question number 10. The missing value of k and the below input output representing a linear function. So it's given that it's a linear function. Okay. So there are some x values and corresponding y values given. But there is no relationship between x and y is not given. The relationship between x and y is not given. Of course, I'll tell you how to arrive at, how to derive this relationship between x and y. I'll tell you later on. But without actually finding the relationship between x and y, can you find the missing value of k? So you have to obviously look for patterns. Okay, look for patterns. So when going from 0 to 1, it gets increased by 1. There is plus 1, plus 1. There is plus 1. Okay. Correspondingly, here there is plus 2. There is plus 2. There is plus 2. So you see a pattern though, right? Do you see a pattern? Do you see a pattern? Do you see a pattern? If you increase x value by 1 unit, your y value will get increased by 2 units. If your change in x is 1, your change in y will be 2. If your change in x is 1, your change in y will be 2. Is that okay? Is that clear from, is this clear from the table? We don't have the relationship between x and y, but we have a table. Do you see the pattern? Do you see the pattern? Do you see the pattern? So let's fill up the missing values, right? So for 0, we have 1. For 1, we have 3. For 2, we have 5. For 3, we have 7. So for 4, we will have 9. And for 5, we will have 11. And this is what is asked for. Of course, there is a pattern. If you keep increasing these values by 1 unit, if you keep increasing these values by 1 unit, the y values keep increasing, changes by 2 units, plus 2, plus 2, and plus 2. So there is a pattern, right? Yes or no? Yes or no? Yes. Yeah. So shall we move on to the next problem sheet, which is the assignment for the current week, for this week. The assignment for this week. The assignment for this week. Please take problem sheet number 21. Problem sheet number 21. Okay. These are the ideas we discussed in last class. Okay. Some scenarios that are represented by linear relationships. Okay. One is direct variation, another is an arithmetic sequence, another is a unit conversion. So we have seen this. Okay, let's try to solve these questions now. Okay, the question is, Derek has already made $20 by selling tickets to an event at school. He has 4 tickets left to sell at $2.5 per ticket. Which of the following below functions represent the total revenue he can generate by selling some or all of the remaining tickets? So he has already made $20. Now, if suppose he is telling, see, he has 4 more tickets left. Okay, but he is not sure whether he can sell all the tickets. Maybe he's selling only 1 more ticket. Maybe he can sell 2 more tickets. Okay, suppose that he is selling X more tickets. Suppose that he is selling X more tickets. For 1 ticket, he is going to generate a revenue of $2.5. For 2 tickets, he is going to generate a revenue of 2 times 2.5. For 3 tickets, it's going to be 3 times 2.5. So in general, if he is selling X number of tickets, he will generate X times $2.5. Apart from the $20 he already has. He already has $20 with him. Apart from that, if he sells X number of tickets, he is going to generate an additional revenue of 2.5 times X. So your revenue, f of X, can be represented as 20 plus X times 2.5, which is 2.5 times X. 2.5 times X. Is this fine for everyone? Is this fine for everyone? 20 plus 2.5 times X. 20 plus 2.5 times X. Is that okay for everyone? 20 plus 2.5 times X. Makes sense, right? Makes sense? Yes. Yes, cool. Next question. Lavida is buying pastries for his son's birthday party. Using the prices on the table, which equation describes the relationship between the total cost and the number of pastries? Do you see a pattern here? Of course, I haven't told you how to generate the function from the table, how to get the expression. There is a standard procedure to get that. We haven't reached there yet. Okay. We are building things slowly. Okay. We are building slowly. Okay. But this question is pretty easy. Just by looking at the pattern, just by observing the table, you can get the relationship between P and C. P and C. Don't you think that there is a relationship here? Don't you think there is a relationship here? Of course, when you go to a shop and purchase things, it is generally a direct variation. For example, say a chocolate cost you $2. $2. So one chocolate is $2. 2 chocolates $4. For 3 chocolates it's $6. For 4 chocolates it's $8. For 5 chocolates it's $10. So that is what we call a direct relationship, direct variation, or direct proportion. Direct proportion. There is a direct proportion. The price is directly proportional to the number of quantities that you're going to purchase, right? The total price is going to be directly proportional to the number of quantities that you're going to purchase. Okay. Now, when you read this question, you have a feeling that this is going to follow the direct proportionality. You have a feeling that this is going to follow the direct proportionality. So in direct proportionality is a special case of a linear function. In direct proportionality, your y will be of the form k times x. There will not be a constant. It will be just mx. There will not be an mx plus c term. C term will not be there. Okay. So in our chocolate problem, it was just 2. The k value was 2. The constant of proportion was 2. Why? Because for every chocolate, it costs $2. For every chocolate, it costs $2. So one chocolate, when x is equal to 1, your y value is 2. When x is equal to 2, your y value is 4, and so on. And even in this question, you see that this is in direct proportion. Why? Because for 3 pastries, it's 8.25. When you double the number of pastries, the price gets doubled. The cost gets doubled. Don't you see that? When you double the input, the output gets doubled. When you double the input, the output gets doubled. Remember, this is not the case with all linear functions. This is not the case with all linear functions. This is not the case with all linear functions. Okay. So in this special case, when you double the number of pastries, when you double the input, the output also gets doubled. This property is there only for functions of this form. A special type of linear functions which we call as direct variations. Okay, direct variations. Okay, so for 3 pastries it's 8.25, for 6 pastries it's 16.5, and when you triple it, the price also gets tripled. Right? How do you check its direct proportion? When you double the number of pastries, the price gets doubled. When you double it, the price gets doubled. When you triple it, so when you double it, this also gets doubled. When you triple it, the price also gets tripled. Okay. That is one way to look at it. That is one way to look at it. Okay. That is one way to look at it. Another way to look at it, for every row, the ratio between output and input, will always be a constant. For every row, the ratio between output and input. Please listen carefully. This is a very important concept. Okay. These type of questions will definitely appear in SAT. Here we are talking about a special case of a linear function which we are going to call as direct relationships or direct variations or direct proportion. Okay. In which there will not be a constant term. Your function will be of the form y is equal to k times x. Okay. So in such cases, if you double the input, your output will be doubled. If you triple the input, your output will be tripled. This is not the case with all types of linear functions. This is a special property attached with these kinds of linear functions. So that is one way to check if it's a direct variation, direct proportion. Another way to look at it is take each row, take the ratio of y by x, output by input. Take the ratio of output by input. So I'm going to take the output by input ratio in each case. Please listen carefully. I'm going to take the output by input ratio. So this is going to be 8.25 over 3. 8.25 over 3. So it is going to be 2.75. You can just plug in the values into a calculator and see that it's 2.75. And in the second row, it's 16.5 by 6. Again, in this case, it's going to be 2.75. In the third case, it's 24.75 by 9. It is going to be 2.75. Okay. Here we have considered C by P ratio. and it came out to be 2.75 every time. Remember, this is not a property which is true for all types of linear functions. In the previous cases, such property was not there. Where are the previous questions? See. In the previous questions, it was not there. For example, take this linear function. Take this linear function. When I doubled it, the output was not doubling. Okay. Because it was strictly not a direct proportion. It was of the form mx plus c. There was another constant added to the output. Here, in this case, what really happens is you're just multiplying the input with a constant to get the output. Okay. You're just multiplying the input with a constant to get the output. So in this case, if you double the input, your output will be double. If you triple the input, your output will be triple. Okay. If you make your input 0, your output will become 0. Okay. That's not the case with the general linear function that we will see. So do you see that the ratio between C and P is always the same in each row? Do you see that? Do you see that? Tell me, please tell me, please tell me. Yes. So we took C over P ratio and it came out to be 2.75 always. C over P ratio was 2.75 always. So how are they related? C over P is 2.75. So your C value is 2.75 times P. So that is our answer. Your C value is 2.75 times P. We could do this easily because it was a direct variation. For general functions, if you have an input-output table, it is not this easy. Okay. But there is a standard procedure which we will soon see. Is that all right? Is that all right? Yes. Okay. The perimeter of a stadium is 1080 feet. Of the following, which is closest to the perimeter of the field in meters? And it's given that 1 foot is 0.3048 meters. So we have seen this idea in the previous class. Here we are talking about unit conversions. So in unit conversions, it's most of the time it's like direct variation. Okay. In unit conversion, most of the times it's like direct variation, but it's not always the case. Okay. For example, the conversion between Fahrenheit and degree Celsius is not a direct variation, direct proportionality. But most of the times it's direct proportionality. Okay. It's given that 1 foot is 0.3048 meters. So your 2 feet is going to be 2 times 0.3048. 3 feet is going to be 0.3048. Yes. 1 foot is 0.3048 meters. 2 foot is going to be 0.3048 meters. Yes. Yeah. So it's given that it is given that 1 foot is equal to 0.3048 meters. So your 2 feet is 2 times 0.3048 meters. Okay. If you have 3 feet, this is 3 times 0.304. Similarly, if you have F feet, your quantity in meters will be F times 0.3048 in meters. Okay, in meters. So this is a shorthand notation for meter. Okay. Okay. So your quantity in meters will be 0.3048 times your quantity in feet. Is that all right? We have seen that we have already seen this in the previous class. Unit conversions most of the time follow a direct relationship, direct variation, or direct proportionality. Yes, cool. Now, in the question they talk about 1080 feet. 1080 feet. So to get the quantity in meters, you have to find 0.3048 times 1080. 0.3048 times 1080. Is that okay? So far, so good? So far, so good? Corresponding to 1080 feet, you have to multiply with 0.3048 to get the quantity in meters. Because 1 feet is 0.3048, 2 feet is 2 times 0.3048, 3 feet is 3 times 0.3048, 1080 feet is 1080 times 0.3048 meters. Right? So far, so good. Please let me know. Please let me know. Yes. Okay, please listen carefully. Okay. Now, suppose that question is in non-calculator section. You are not allowed to pick up a calculator. You are not allowed to pick up a calculator. What will you do? Okay. So this question is very interesting because, when you look at the options, these are not very close numbers. These numbers are far apart. Okay, these are not close numbers, which means you can afford to do some approximations. You can afford to make some approximations, right? Please get this point right, okay? You look at the options are far apart. They are not very close together. So without actually doing the real math, I am going to make an approximation. Okay, because doing this multiplication is going to take some time. Doing this multiplication is going to take some time, right? Doing this multiplication is going to take some time. If you do not have access to calculator, this will be time consuming. So what I'm going to do is I'm going to make an intelligent approximation. Instead of 1080, if it were 1000, so this is approximately 1000. If it is 1000, the number will be approximately 304.8. Do you understand this? Now, instead of 1080, we have taken 1000. So you have two ideas from this. One, the answer will be very close to 300. Two, the answer will be slightly above 300. The answer will be close to 300, but slightly above 300 because instead of 1080, we have taken 1000. Does this make sense? Does this make sense? Does this make sense? Yes. Yes. So these are some of the sneaky approaches, some of the tricks, some of the strategies that you should keep in mind. Because, it is going to be a painful thing. It is going to be a frustrating thing, multiplying these two numbers. If you do not have access to calculator. But see, the question also gives us a hint. The question says closest value. Okay. So they are also not really worried about the exact answer. They are also not really worried about the exact answer. They are also looking for some approximate answers. Always remember this. Always remember this. If the question does not really ask for a exact value, okay, and if the options are far apart, you can afford to make an approximation. So what will be the answer from these options? What will be the answer? The answer has to be close to 300, but slightly above 304. Slightly above 304. The answer is clearly 330. The answer is clearly 330. All right. Just give me a minute. Hello. ഞാൻ ക്ലാസ്സിലാണ്. ഞാൻ 8:15 വിളിക്കാം കേട്ടോ. 8:15 ഫ്രീ. Yes. Cool. Yeah. Let's go to the next question. You travel 21 miles every day on your car. Suppose you are traveling to school and coming back on your car. Okay. You are traveling every day for 21 miles. Before starting your journey today, you notice that the odometer reads 3087. What will be the odometer reading at the end of 21 days? Okay. So before starting the journey today, it is 3087. So at the end of first day, it is going to be 30 at the end of today. At the end of today. Okay. At the end of today. Today before starting the journey. Today before starting the journey. Suppose you're about to begin your journey and before starting the journey, you notice that it is 3087. So at the end of first day, it is going to be 3087 plus 21. At the end of second day, it is going to be 3087 plus 2 times 21. Right? Don't you see that there is a pattern? Don't you see that there is a pattern? Is there a pattern? See, every day you're traveling 21 miles. And before you notice the reading of your on your odometer, the reading says 3087. Okay. So before no, you don't have to really write that. At the end of day one, that is today, the reading will be 3087 plus 21 because you would have traveled 21 miles going to school and coming back. At the end of day 2, it is going to be 3087 plus 21 times 2. Why? Because you're adding one more 21. You're adding one more 21 to that. At the end of day 3, it is going to be 3087 plus 21 times 3. Right? And there is a pattern. Don't you see that there is a pattern? And this pattern is what we call an arithmetic progression. We have seen this in the previous class. An arithmetic progression is something that starts from one number and you keep adding some constant number to those number to the initial number to get a sequence of numbers. Okay. So that is what we call an arithmetic progression. And arithmetic progression is a special case of a linear function. Okay. So that is what we saw in the previous class. So at the end of day 4, it is going to be 3087 plus 21 times 4. And similarly, moving in this, following the same pattern, we have to find the reading at the end of 21 days. At the end of day 21. At the end of day 21. This is going to be 3087 plus 21 times 21. 3087 plus 21 times 21. Is that okay? Yes. So this is 3087. 21 times 21 is 441. 441. Okay. We just do the math and get the answer. That is going to be 3538. 3528 is the answer. 3528 is the answer. Of course, for this 21 times 21, there is a pattern. Okay. 12 times 12 is 144, and 21 times 21 will be 441. Okay, the digits get reversed. Just like when going from 12 to 21, the digits get reversed. When going from 12 square to 21 square, the digits gets reversed. It's not always the case, but for 21, that property is there. Okay. Okay, so please, if you have not fully solved this sheet, please try to solve the sheet. I'll try to share some more problems with you over this week. Okay, please spend some time. The exam may be, maybe 1 year from now, but you have to spend sufficient time, at least half an hour, 1 hour per week on this. Okay. See you in the next class. Thank you. Yeah, bye.